Hello everyone and welcome to the wonderful world of complex numbers. Today we are diving into a specific way of representing these fascinating numbers, the polar form. You might already be familiar with complex numbers in rectangular form written as a plus bi, but the polar form offers a different perspective using concepts like distance and angles. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to lecture 5 where we are starting with the polar form of complex numbers. Now before I go ahead with this series of complex analysis, here is a quick recap on the earlier 4 lessons what I have covered. Now earlier when I started, it was a little bit gap in recapping all those things which I have done. So we have dealt with what is a complex number. There is a video on the history of complex analysis and it carries quite a detailed history of complex analysis from the evolution of numbers to a very fascinating history. I have also covered what is called a modulus of complex number, relation between argument and modulus. What is the difference or relationship between complex and imaginary number? What is a complex plane? I have also given few simple examples to demonstrate operations with complex numbers and what is a complex conjugate. So all these are being covered in the earlier 3 to 4 lectures, and if you want, I've already given it in the description box, all the links, plus you will find it in the I button. So you can just go ahead, and those who are a little bit curious about the history of complex analysis and what is actually complex analysis, how does it make a significant difference in the industry, you can have a look. So today we will start with the polar form of what is called the complex numbers. Now you are all aware about what is called the rectangular form. So this is the standard way where a complex number is written, and this is the graphical depiction. Whereas polar form, in contrast to the I would say to the a rectangular form, is represented z using its distance from the origin and the angle it makes with the positive real axis. So here is the polar form. So the reference is called the pole. The ray which is directly originating from the pole to the reference direction is called the polar axis. The distance from the pole is called, you can call it radial coordinate or simply radius, and the angles in polar notation are actually denoted by degrees or radians, and we will actually deal with those what are called degrees and radians. Now before I go ahead and explain the mathematics of polar form, it is important for all of us to know how the development of complex numbers, I would say the polar coordinates, actually took place. In the earlier videos, I have dealt how complex analysis and the numbers actually originated. Here is a development of polar coordinates, and we have to go back to none other than the British polymath Isaac Newton. Now in Methods of Fluxions, which was published around 1671 and written in 1671, published in 1736, Newton examined the transformation between polar coordinates, which he referred to as the 7th manner for spirals, and 9 other coordinate system. So you can say that a total of 10 coordinate system which is Isaac Newton perceived and which was referred to in the Methods of Fluxions in his work. Now in this journal, Acta Eruditorium in 1691, Jacob Bernoulli used a system with a point on a line which is called the pole and polar axis respectively. So coordinates were specified by the distance from the pole and the angle from the polar axis. However, Bernoulli's work extended to finding the radius of curvature of curves and is expressed in these coordinates. But still the question comes that who actually coined the term polar? So the credit of the actual term for polar coordinates goes to this gentleman Gregorio Fontana, an Italian mathematician who has coined this term in 18th century in his Italian writing. So Gregorio Fontana was actually born as Giovanni Battista Lorenzo Fontana around 7th December 1735, was an Italian mathematician and a religious of the Piarist order. He was a chair of mathematics at the University of Pavia. Now the term actually appeared in English in George Peacock's 1816 translation of Lacroix's differential and integral calculus. Alexis Clara was the first to think of polar coordinates in 3 dimensions, and it was this genius Leonhard Euler who was the first to actually develop them. This actually gives you an idea of the development of polar coordinates. However, there are many other historical figures which I have omitted because our main purpose is the mathematics of polar coordinates. So as you see that in this figure, that a polar coordinate system is superimposed, for example, in a complex plane, which is this one, with polar axis coinciding with the positive x-axis and the pole O at the origin. Then what we can say that is that x, y, r and theta are related by x is related to r cos theta and y would be related to r sin theta. So these equations enable us to express a non-zero complex number which is z equal to x plus iy. Similarly, I have underlined it in red so that you can find it in the diagram also, as z equals to r cos theta plus r sin theta, or we can say it represented as z equals to r cos theta plus sin theta, and we call this particular form as the polar form or polar representation of the complex number z. Now as you can see in this figure that we see that the coordinate r can be interpreted as something which is called the distance from the origin to the point xy. In other words, we shall adopt the convention that r is actually non-negative, or I would say never negative, so that we can take the argument and it looks like something like this. The modulus, that is r equals to mod. Now the angle theta which is formed on the left hand side of the diagram, as you can see, has got certain characteristics. First is that theta will always be measured I would say in terms of radians. Theta will I would say positive. It will measure a positive number when measured counterclockwise and negative when measured clockwise. Theta is the argument of z, and that is why we can write is something as theta equals to arg z. Now note here this arg, which is the argument. In some literature it will be written in italic, in some it will be non-italic, so it doesn't matter. It is actually the arg z. So an argument theta of a complex number, remember that this theta must satisfy this form, that is cos theta equal to x by r, and sin theta should be equals to y by r. So this actually shows that r should not be negative and theta is measured in this, and it must satisfy something like that. Now this is something which I would like to explain, that you see that an argument of a complex number which is z is not unique, since cos theta and sin theta are two periodic. Now what do I mean by that? You know that complex numbers are actually visualized as points on a plane where the horizontal x-axis represents the real number and the vertical axis represents the imaginary number. Now the argument of a complex number z is the angle between the positive real axis and this one, I would say the between the positive real axis and the line connecting originating to the points this one. So cos theta and sin theta are trigonometric functions which will obviously repeat for every 2 pi. That means we can say that an argument of a complex number is not unique, since cos theta and sin theta are what? 2 pi periodic. So in other words, as you can see right at the bottom, I have written that theta 0 is an argument of z. Then the necessary angles theta 0 would be plus minus 2 pi, theta 0 would be plus minus 4 pi, and so on, are also arguments of z. So it actually shows that when you make a kind of a circle, I mean to say when you are rotating it on kind of a 360 degrees, it will give you the same values, and that is why it comes in a kind of a periodic. Now this example which I have given is not very much clear, I understand. Let me show you with this kind of an example. So let us suppose that if I try to express this in polar form, then with x equal to this we get y equals to 1, and from here I can calculate the value equals to 2. Now we know that y by x will be equal to this value, which gives the tan inverse which is equal to 1, and obviously it leads to pi by 6. Now this is an angle which is on the terminal side of the first quadrant. What do I mean by that? Let you see this diagram, you can understand. So here is minus square root of 3, here is minus 1. So pi by 6 this one pi by 6 is on the terminal side of the first quadrant. So what we do is that we take a solution of tan theta, which is equal to this one, which leads to 1 upon square root of 3, sorry, and theta can be our argument of this, which can be calculated as 7 pi by 6. Now taking it further forward, what we can find is this one can be represented as this, which further can be represented using this equation z equal to, it is the form of r cos theta plus I sin theta, we can take into this. Now this particular problem is something which the mathematicians solved using a concept which is called a principal argument. Remember, there is no UE, it is just ARGU. So when we talk of principal argument, what do I mean by that? Now you see this notation which we have used, arg z, is used to be is used to designate what we call an arbitrary argument of z1. What does that mean? It means that arg z is a set rather than a number. That means in particular the relation arg z1 equals to arg z2 is not an equation but an expression of two sets. So we can say this is a set rather than a number. So as a result, two non-zero complex numbers, if I suppose that cos phi 1 and I sin phi 1 and so on, plus and this one r2 cos phi 2 and plus I phi 2 are equal only and only if there are two conditions which will satisfy. One is obviously r1 equals to r2 and phi 1 and phi 2 equals to 2 plus 2k pi, where k is obviously an in the family of the integer. So in order to make, I would say, the argument of z a well-defined number, we sometimes restrict it within that limit of, say, minus pi to plus pi. And these special choices are basically what we called, what is called the principal argument, or the main branch of the argument is written as capital ARG z. So that ARG, small ARG z is something different, and here you can see the principal is something which is RZ. Now there is no general convention about the definition of the principal value. Okay, I will just come forward with this example. I equals to, for example, if z equals to I is equals to 1, suppose we take it, then from this figure what we can see is that arg I, remember this is not the principal argument, earlier argument I, r can take a value of pi by 2, 5 pi by 2, minus 3 pi by 2 and so on, right? But arg I, this one, if I take this one, which is pi by 2, here, the red one, this arg equals arg I, it will be equal to pi by 2. So what we can say from here, that the argument of minus square root of 3, which is this one, which lies within the interval of what? It would lie within the interval of minus pi to plus pi. And the principal argument of z is arg z, which is this one, which is equals to, I have not calculated, but you can calculate pi by 6 minus pi, which equals to minus 5 by 6. So using arg z, we can express the polar form, I would say the complex number, in another alternative form, and this alternative form is something like this. Right, so this can be, and remember that this relation between arg z and the principal arg z are related by this one, which is this equals to this, and where n should be ranging between 0 plus minus 1, 2 and so on. So if I take an example, for example, arg I equals to pi by 2 plus 2n pi, n, I have already given the value ranges. So for the choices of n equals to 0 and n equals to minus 1, that means this particular equation, if I go by the, this particular part, that this equation, it gives arg I equals to pi by 2 and arg I would be equals to minus 3 pi by 2. This is how actually we calculate. So this video pauses over here. It is a short video, but I have actually given you a fair good idea what is the polar form, how it evolved, some quick examples, and what is principal argument. However, polar form will have another video where we will be talking about the plus minus, the operations and certain other things. So that's all for today's video. I thank you immensely for taking up your time and watching this. If you have liked this video, please do not forget to hit on the subscribe and click on the bell icon to get all the notification from Physics for Students. You can write to me for any issues, or if you want to talk at this email ID. Don't forget to like and subscribe to my other channel where I put up exclusive videos on general theory of relativity, and you can follow me on my Facebook, LinkedIn, Instagram and Twitter account. That's all for today's video. Physics for Students will be soon back with more interesting videos, and most importantly, the complex analysis series will keep on rolling and going until you are happy and I am happy. Till that time, goodbye, and may the good Lord be with you.